Understanding p-values. We use our p-value to measure how surprised we are with our result. Recall, the definition of p-value is the probability that if the null hypothesis were true, we would get a statistic as extreme or more extreme than the observed test statistic. Now, this definition is confusing, so in this video we're going to talk about what it means. Let's look at an example similar to something we've seen before. So suppose we spin a coin 20 times and observe how many times we get heads. Let's say we're interested in whether or not the coin is fair. Has it been weighted to make it more likely it's going to land on one side? Or is it just a fair coin where it's 50% chance you land on heads, 50% chance you land on tails? Let's say we do this and we get 7 heads out of 20. Then our observed outcome is 7 out of 20 heads. In other words, p hat is 7 over 20 or 0.35 if you put it into your calculator. Now, the null hypothesis of this scenario is the neutral, skeptical statement about our population parameter. In other words, it's the statement that if we spin the coin is fair and it's a 50% chance we land on heads. In other words, p equals 1/2. The alternative hypothesis is the research hypothesis. It's a statement about the value of a parameter we intend to demonstrate is true. In other words, the coin is not fair. And in this case, p would not be equal to 1/2. So its probability is not 1/2 that the coin lands on heads. Now, in another video from 8.1, we found a test statistic for this example. In particular, we found the test statistic to be z equals -1.34 using the formula below. So you can go back to this video in 8.1. It's the test statistic video if you want to see how this computation is done. Now, knowing that our test statistic is -1.34 helps us understand p-value. How? Well, to find the p-value, by definition, we're supposed to consider if the coin were really fair, what's the probability that we would get a test statistic as extreme or more extreme than the one we found? In other words, -1.34. Now, how do we understand what this means? Well, it means that we get we spin something that gives us a value even farther away from the mean of 0 than -1.34. Now, if you're looking at this picture here, we have a probability distribution for the scenario of spinning the fair coin 20 times, what we might get. On the x-axis here, you're looking at a couple of z-scores. Now, the z-score right here is -1.34. It's the one we found for it goes with spinning 7 out of 20 heads. Z-score of 0 is spinning 10 out of 20 heads. That is the expected value. 10 out of 20 is 50% chance of getting heads. And so pretty much every point along the x-axis here would go with spinning a certain number of heads, where if you spin more than 10 heads out of 20, you would go to the right. If you spin less than 10 heads out of 20, you go to the left. Now, all the things that we could get if we spun the coin 20 times are listed below. You could get 0 heads, 1 head, 2 heads, 3 heads, 4 heads, 5 heads, all the way up to maybe 20 heads. What are you guys looking at here? Well, the values that are highlighted in red, those are the ones that are more extreme or as extreme as spinning 7 heads out of 20. So like the mean, if the coin is fair, like our expected number of heads would be 10. And if you got 11 or 9, that's not that extreme. It's pretty expected if the coin really were fair. If you got 8 or 12, that would also be like, not surprising. But if we got 7 out of 20 heads, the number of heads that would be like as extreme or more extreme than 7 would be like if we got 7 or 6. Spinning 6 would be a more extreme result, even farther away from 10. Spinning 5, 4, 3, 2, 1, 0, also more extreme than spinning 7. And then we can go to the other side too. So if we're from 13 to 20, this range away from the middle 10, that would also be like as extreme or more extreme than spinning 7 out of 20 heads. Now, let's look at this picture here. We have shaded all of the area that is outside of the range of -1.34 as a z-score away from 0 on both the left and the right. So this one right here starts at +1.34. Now, what is our shaded area? The shaded area represents our p-value, where p-value is the probability that we are going to spin 7 or fewer heads or 13 or more heads. where the cutoff values are 7 and 13 because they're like equal distance from 10. And so in the picture, this shaded area is our probability or our p-value. Now, what is it if we actually use technology to calculate it? It's 0.1797. Now, what's the connection between like how much area you shade, or the size of the p-value, and how far we are from the mean? Let's look at another picture to understand that better. So what you guys are looking at is a bunch of different z-scores, and they each go with rolling a specific number of heads out of 20. So right here is the one we were just looking at. This is what you have if you roll 7 heads out of 20. In this case, we have a z-score of negative 1.34, and we shade everything that's as extreme or more extreme than spinning 7 heads out of 20. And our p-value is 0.1797. So take a minute to think about if you think that we would have more or less shaded area if we had maybe fewer heads than 7 that we spun. So say we spin only 4 heads out of 20. If the coin were fair, this would be like super surprising. It's really far from 10. It's really far from spinning 1/2 of the coins are heads, or 10 out of 20 are heads. In this case, the z-score is so far away from the one that goes with 10 or 0 that you can't even really see any area shaded. This goes with a p-value of 0.0073. Now, this would be very surprising, and so that goes with a small p-value. It means if the coin were fair, we would not expect this to happen, or we'd expect it to be very likely. Now, compare that with spinning 8 heads out of 20. Now, we would be less surprised if we got 8 heads out of 20 because 8 is pretty close to 10. If the coin were fair, this would not be very surprising. This goes with a bigger p-value. So in this case, the p-value is 0.3711. And you can see there's more shaded area. So the shaded area on the left corresponds to spinning 8 heads or less. On the right, it corresponds to spinning, let's see, 12 heads or more. So that would be like as extreme or more extreme than 8, but on the other side of 10. So the idea here is that like the closer your outcome is to the mean, or like what you would expect if the coin were fair, the larger the p-value is. Now, what happens is we go on when we do our hypothesis test to figure out our p-value and then compare it to a certain number. Oftentimes it's 0.05. And we decide to basically like determine if we should reject the null hypothesis based on comparing the p-value that we got to a number that's usually 0.05. Or you might be given some other one. So let's look at some of these p-values that we got here. So in particular, take a look at the one where we get 8 heads out of 20. Now, if the coin were fair, we would not be surprised by this, right? And our p-value is 0.37. Usually we use the number that we compare this to is 0.05. And since 0.37 is not smaller than that, we would in this case not to reject the null hypothesis. We would think, well, the coin probably is fair. Now let's compare that to spinning 4 heads out of 20. If you spun 4 heads out of 20, you're probably going to think, whoa, that's very unusual. I'm surprised this would happen. And in this case, we would get a p-value of 0.0073, which is smaller than 0.05. So in this case, we would reject the null hypothesis if we were using a significance level of 0.05 because our p-value is smaller than that. Now, we're rejecting the null hypothesis that the coin is fair for a couple reasons. One, because our rigorous way is to compare the p-value to significance level. And in this case, we would have a small enough p-value to reject the null hypothesis. And then also, you can think about it as if, well, we only got 4 heads out of 20. That's like really far away from getting 10 heads out of 20. I'm starting to be skeptical of this coin. I think maybe it's not fair. Okay, now, one last thing to say about p-values. We have this phrase, as extreme or more extreme, and it's going to mean different things depending on if you have an alternative hypothesis that's two-sided versus an alternative hypothesis that's one-sided. Now, when you have a two-sided alternative hypothesis, we also call it a two-tailed p-value. When we have an alternative hypothesis that's one-sided, so it's like a less than or greater than symbol here, with the h sub a. That's called a left-tailed p-value or a right-tailed p-value. Now, the reason is because when we go to look at the probability distributions and shade the specific probabilities that go with these p-values, for two-tailed, when you have h sub a is not equal to p naught, you're going to shade both to the left and to the right, because our alternative hypothesis is just that p is not equal to the standard one that we thought it was. And it doesn't matter if it's greater than over here or less than over here, we just know they're not equal. Now, for an alternative hypothesis that's like p is less than p naught, we're guessing that our p is less than the typical one, and our probability is gonna be everything shaded to the left. This is called a left-tailed p-value. And then it's the other way for an alternative hypothesis that is to the right. So you would only look at the p-value would only be the shaded area to the right. So I guess the short of it is this: when you're calculating your p-values, which we'll do when we do our hypothesis testing examples, for ones that are two-tailed or p is not equal to, you're going to look for areas that are shaded to the left and the right of a z-score. And then for one-sided, so p is less than or p is greater than, you actually are only looking at the shaded area to the left or the right to calculate your actual p-value. Okay, this will maybe come together once you start doing hypotheses tests, which is what the next two videos are about.